The Doppler effect is one of the more fun phenomena of waves in terms of experiencing it in everyday life, and just looking for it. Once you know what it is, it's pretty cool to think about. So anyways, let's just get started with some basics here with waves and establish our equations that we haven't used in a few weeks. All right. Just to recall, the wave equation that we use tells us the speed of the wave. All right, it's just its wavelength times its frequency. This is also the same as writing the wavelength over the period, and we could also rewrite this. The period is just equal to lambda divided by v. This is all very useful when we finally do derive Doppler effect equations. Okay. So the Doppler effect, just to remind you guys, is a change of frequency of a wave due to the movement of the source or the observer relative to the medium of the wave transmission. Okay? So what this results in, right, for sound, we get a change in pitch, and with color, we get it, with light, we get a change in color. Okay? So let's get started. I'm going to show you the derivation. There is no space in the notes for this necessarily, but I like to do it just that you guys can see where it comes from. And if you want to take these notes, that's fine. All right. But it's just going to show you what is happening exactly. So we take any old circular wavefront, okay, emitting equally out in all directions, and the distance between successive wavefronts, this right here, this is our wavelength, lambda. Okay, and I'm going to call lambda d right here, the distance that the wave will have traveled. And there's a reason for this. All right. So what we're going to say is that this same source, all right, is now going to have moved. Okay. So this first example that we're looking at is the source moving. Okay, the source of the sound. And there's some observer over here to the right, we'll say, right? But when the source has moved, okay, we still have this first wavefront that it emitted, all right, as in the image above. But what happens is that the next wavefront that's emitted is a little bit closer to it, okay, if the source is moving towards that wavefront. So we now have a new wavelength, we'll call it lambda prime, all right? And the distance that the source has moved we'll call d sub s, okay? And d sub s is going to be equal to the speed of the source, u sub t, times the period, right? Which is the time in between which we'll be emitting waves. Okay, so again, the distance the source has traveled is how fast it's traveling times the period. Okay, and that's how far it's traveled between each time it is emitted a wavefront. And that's the distance it's traveled. Excuse me. So, okay, let's say that you're a source that's moving towards the observer. Towards the observer. All right. Your new wavelength, lambda prime, is just going to be equal to d, which is the distance that the wavelength traveled up here, all right, minus the distance that the source has traveled. Okay, we're substituting our values here. Lambda is just d, all right, and this is going to be equal to us times t, all right. So if we remember that the period is just equal to lambda divided by v, we substitute that in, that's from the previous slide, we end up with this, lambda all over v. And since both terms share lambda, use the distributive property, we end up with lambda equals 1 minus the ratio of the speed of the source to the wave. Okay? And this is the first equation that we're going to have for the Doppler effect. Right? This is the new wavelength, okay, based on the speed of the source and the wave speed. We may also have a situation where the source is moving away from the observer. If this is the case, okay, the new wavelength is going to be equal to the original wavelength plus the distance that the source has moved, all right? And we're just going to rewrite all of this like this, do the same substitutions that we did before, and when we do all of that, what we end up with is this, okay? So you see we have two different equations. In the previous page, there's a minus sign in that term, and here there's we're adding, all right? So again, let's go back to the source moving towards the observer here, okay? We're going to add a small piece to it. The new frequency that's observed with the source moving towards the observer, f prime, is going to be v divided by lambda prime. Remember, v is determined by the medium, so that's not going to have change. All right, so we're going to substitute in lambda prime here, and what we end up with, 1 minus u sub s over v, like this. Okay, there we go. V all over lambda is just f, okay? So we have f all over this term right here. All right? So when we rewrite this, okay, do a little bit of fun algebra. Here, let me just rewrite this one over here. F. Okay? What I'm going to do here is I'm going to say that, here, I'll show you. Having trouble putting math to words here, kids. Sorry. 1 over v. Show you the way I want to look at this. That's right. 1 over v right here. And that's going to give us this v minus u sub s there. That's what I want, okay? So saying 1 is v over v, give us that common 1 over v term between both of those, all right? And so what this is going to leave us with is f, right like this, f times v all over v minus u sub s, okay? And so this is our equation for the shifted frequency of a source, okay? So source towards subtract, this is an acronym, all right? Source towards subtract. What this tells us is that the formula for the shifted frequency, all right, we have to be subtracting the speed of the source, okay, to calculate that. So what does that tell us that the new frequency is going to be? Well, if we look at the math here, it's going to have to be f is going to have to be greater, f prime is going to have to be greater than f, okay? So it's a higher pitch. And this makes perfect sense. When the source is moving towards us, it has a higher pitch. Have you ever noticed an ambulance driving towards you, okay, emitting a sound? You're going to hear that sound at a higher pitch until it passes you when you hear the pitch drop, all right? So this is going to be the equation we use to calculate that shifted pitch. If we do the same math, okay, for the source moving away, okay, the source moving away, what we end up getting here, okay, I'm just going to skip all of the algebra. You guys can do it. It's going to end up looking something like this. Okay, so source, all right, moving away this is the equation for that. So we know it's just the opposite. We just add the speed there. Okay, so we know in this situation f prime has to be less than f. Okay, so it's going to be a lower pitch. All right, so the last example, the last derivation I'm going to show you here, all right, has to do with the observer moving towards the source, all right? So when the observer is moving towards the source, it looks a little bit different here. I'm going to draw this. We still have our wavefronts being emitted, all right, like this. This is our lambda, all right? These wavefronts are moving forward with speed v. And what we have now is our observer over here. This is our observer, this is our source. The observer is going to say, we're going to say moving towards, so observer moving towards. At speed u sub 0, or u sub o, excuse me. And so what we end up seeing here is that there's going to be a shifted frequency, and then that shifted frequency is going to be equal to f prime is equal to v prime all over lambda. Okay, so lambda hasn't changed, but what has changed is the relative speed of the wave. All right, because we are now moving relative to the medium. So that relative speed, all right, through the wave is the relative velocity. We're going to be adding the speed of the observer. Okay, since both velocities will be moving relative to each other. All right, and what we end up with, okay, let's see here, is f prime is equal to v over lambda plus u naught, or uo, excuse me, all over lambda, and this is just f plus, all right. And we can substitute in our definition of lambda here, all right, and we get, let's see here, f over v times u sub 0, all right, and f, there we go. So this looks like our previous formulas here. We have a little way of remembering this, a little mnemonic, and it's observer towards add, OTA, okay? The observer is moving towards the source. We add the term here in our parentheses. Now it's going to help you remember these formulas, all right, on the test, as you will have these formulas, I think, in the IB data book. If you check there, at least one or two versions of these are there, but they don't tell you what goes with what, okay? So if we had a different situation with the observer moving away from source, the frequency will shift a little bit differently, all right? All right, so with the observer moving towards the source, we see that f prime, again, obviously is greater than f, and here moving away, prime is less than f. This deals with, it makes perfect sense, actually. I mean, it's really just the relative motion that you need to be thinking about here, you know, in terms of the same idea of the frequencies changing. All right? Okay, so let's talk about these equations that I've just given you here. Let's start with the Doppler effect for a source moving towards an observer. Actually, you know what? No, let's continue this in the next video. That'll do it for now for the derivations. I'll give you the properties of all these equations and some examples in the next video.